Welcome to you all to this MOOCs online video course Theory of Yarn Structure. In the last class we started with module 4 helical model of fibers in yarns. As you know, helical model is a very popular and oft quoted models in the theory of yarn structure. This model basically explains the number of fibers present in the cross section of yarn. It also explains the phenomenon of yarn retraction, and finally, it talks about limit of twisting. After insertion of certain amount of twist, if you still go on increasing your twist, then this twist do not go inside the structure. So, it gives a very different kind of structure. So, there is some certain twist called limit of twisting. So, this model also explains that. Now, in the last class we talked about how to determine number of fibers in yarn cross section based on helical model. Today we will continue with helical model and we will study yarn retraction. What is yarn retraction? Yarn retraction refers to shortening of yarn length due to twist. You might have observed that if you twist a parallel bundle of fibers, then after insertion of twist the length of the resulting yarn decreases. So, this phenomenon is called yarn retraction. Today we will learn the principles, what governs yarn retraction and the associated relationship on yarn retraction. So, let us start yarn retraction. Yarn retraction is schematically shown in this figure. This is a parallel fiber bundle or non twisted fiber bundle. So, let us write here non twisted bundle, and this is the result after twisting. So, this is twisted bundle. Now, these two bundles, non twisted as well as twisted, they have certain characteristics. Let us establish those characteristics first. The first characteristic is length. What is the length of this bundle? Is zeta naught. What is the length of this twisted bundle? This is the length, is zeta. Right. So, what is yarn retraction? Yarn retraction is defined by change in length divided by original length. So, what is the change in length? Zeta naught minus zeta, and what is the original length? Zeta naught. So, if we simplify, we obtain this expression. Let us use a symbol delta to denote yarn retraction. right. Then we come back to our characteristics of the bundles. Second characteristics is number of fibres. Suppose there are n number of fibres here in the non twisted bundle. After twist also there will be n number of fibres, because fibres cannot fly out of yarn. So, n number of fibres, right. Then volume of fiber, suppose initially the volume was V naught and after twisting fiber volume in yarn may change, may not change, we will see what will happen. V, right. Then mass of fibers, suppose initially fiber mass in the non twisted bundle was m, this will remain same in twisted bundle. So, this will remain same. Okay. Then count, what is the count of this non twisted one? Mass per unit length, and this count will change because length is changing. Right. What is the relation between T naught and T? T is mass by length. Let us write this as so. What is this? This is T naught, and what is this? This is 1 minus delta, is not it? So, T is equal to T naught divided by 1 minus delta. So, this is the relationship between counts of non twisted bundle and twisted bundle. Twisted bundle is yarn. Okay. We will continue with this further in order to establish a few more characteristics. Number of coils. Number of coils initially here is 0 and here it is suppose NC, right. Now actually let us imagine that this number of coils was also present here, but in a latent manner, right. So, what we think that these number of coils are present also here. So, number of coils let us write here as NC. You can write here imaginatively this number of coils was latent, they were expressed later on, right. So, then latent yarn twist, yarn twist is Z naught, number of coils per unit number of latent coils per unit length. Okay. And here it is real yarn twist. Z is NC by this. Now, we can write it as NC by this manner. What is this? This is your Z naught, and what is this? You remember yarn retraction was 1 minus final length by original length. So, 1 minus delta. So, this is the relationship between two twists. Now, this is imaginative, because it is parallel fiber bundle, it should not have any twist. However, we imagine that this was latent twist. This twist will be expressed after in the yarn. So, that is why we use this word latent yarn twist, and here we use real yarn twist. Okay. Then similarly, if twist is there, twist coefficient will be there. Latent twist coefficient. What is twist coefficient? Alpha naught twist into initial count, and here real yarn, real twist coefficient is alpha is equal to Z root T. Okay. What is the relation between latent twist coefficient and real twist coefficient? What is the relation between alpha naught and alpha? Let us establish that. So, alpha is Z root T. Let us substitute. What is Z? Z is Z naught 1 minus delta here, and what is your T? T was expressed earlier. T was, you remember, T naught by 1 minus this, but this is square root. So, Z naught T naught 1 minus delta to the power 3 by 2. So, Z naught T naught is equal to alpha naught 1 minus alpha to the power 3 by 2. Right. So, you remember three relations that we will use later on. First was T naught by 1 minus retraction, second was Z naught 1 minus retraction, third was alpha naught 1 minus retraction to the power 3 by 2. So, these three relations we have derived, and we will use them in this module subsequently, right. So, we have established all characteristics in a non twisted bundle as well as in a twisted bundle, right. So, now what we will do? Now, we will have one important assumption. What is this important assumption? The important assumption is that the relation between V and V naught. You remember what was the relation between V and V naught? relation between V naught and V. What is V naught? V naught is the volume of fibers in a non twisted bundle, and what is V? V is the volume of fibers in a twisted bundle. How is the relation? Let us assume they are equal. We will see later on the consequence of this assumption. So, our assumption is V naught is equal to V, right. So, what is now V naught? V naught is the volume of all fibers. How many fibers? N. And what is the volume of one fiber? What is volume? Cross sectional area into length. They are parallel fiber bundle. So, what is cross sectional area? Small s. And what is length? Zeta naught. So, this is V naught, right. And what is V? V is the volume of fibers in the twisted yarn. They are not parallel, right. So, if they are not parallel, then that is the total substance cross sectional area, capital S, into length. What is length? Zeta, right. Then we can write that S n is equal to zeta by zeta naught, is not it? And what is capital S by N? Total substance cross section area of the yarn divided by number of fibers, that is equal to mean sectional area of fiber. You remember in module 2 we discussed about that. So, this is equal to this, right. And what is this expression? S by A star bar. This is coefficient K n. All we discuss in module 2, module 3. And what is this? This is 1 minus retraction. Why? You know the definition of retraction, change in length by original length. So, this is this. So, a very important relation we obtain here, coefficient K n is equal to 1 minus retraction, right, or we can write retraction is equal to 1 minus K n, right. So, retraction is 1 minus K n, all right. Now, K n was derived by this form. right. Sorry, 1 minus k n lambda. So, this k n we derived in the last class. Okay. Now, we need to work on this expression, so that we find a measurable expression for delta yarn retraction. How we do it? Let us see. One plus pi d z square plus 1 right, minus 2 by pi d z squared into 1 plus pi d z square minus 1 into 1 plus pi d z square plus 1 divided by 1 plus pi d z square plus 1. So, what we did basically? We basically multiplied and divide by this expression. Here it will cancel, so 1 will come, minus here this will cancel, so this expression will come. Okay. Right. Let us see the consequence of this. This will remain as it is, square plus 1 minus 2 by what will be this? This will be 1 plus pi d z square minus 1, is not it? So, this 1 will cancel, pi d z square will cancel, this minus 2 will be there, plus 1 is here. So, what we will obtain? 1 plus pi d z square minus 1 plus pi d z square plus 1. Nice form, is not it? Right. Let us make it more nice. How we can do it? What is pi d z? Pi d z is tangent of beta d. So, if we continue, 1 plus tan square beta d minus 1, here it is 1 plus tan square beta d plus 1. What is 1 plus tan square beta d? Sec square beta d. Square root of sec square beta d is sec beta d. So, write sec beta d minus 1 by sec beta d plus 1, and sec beta d is 1 by cos beta d. So, what we obtain is delta is equal to 1 minus cos beta d by 1 plus cos beta d, right. We can further work on it. What is 1 minus cos beta d? 2 sin square beta d by 2. What is 1 plus cos beta d? 2 cos square beta d 2. So, tan square beta d by 2. Very nice expression, tan square beta d by 2. So, this is the expression for yarn retraction. Now, what we learned? We learned that yarn retraction is related to the coefficient Kn, which is further related to twist angle of surface fibers. How is the relation? Yarn retraction is tangent square half of twist angle of surface fiber. So, basically this is how twist dictates retraction. Because of twist, length shortens. So, this is yarn retraction. So, once the twist is inserted, finally it is the angle of surface twist fiber that finally determines yarn retraction. This is what we understand. Okay. Now, as I told you, helical model explains 3 important things. One, it helps us to determine number of fibers present in yarn cross section. Second, it explains the phenomenon yarn retraction. Third, very important from practical point of view, it gives us an idea of limit of twisting. Have you ever tried experimentally to find out whether limit of twisting exists or not? You can do it easily. Go to a textile testing laboratory, there is yarn twister, mount an yarn and try to increase the twist. Have a magnifying glass and look at the structural change in the yarn. After insertion of certain more twist, you will see the fiber coils are not going inside the yarn, rather they basically bulge. So, yarn structure bulges. So, there is a limit of yarn twisting. Beyond that, the structure does not absorb the twist. So, it basically goes outside. That is why you will see certain destruction of yarn structure, certain bulging of yarn structure. So, that is limit of twisting. That means practically it exists. Can it be explained scientifically? Yes, it is possible. Today it is possible to explain scientifically. By using helical model, we can explain this phenomenon scientifically. So, that is our third objective under this module, to know about limit of twisting. So, we will now proceed towards that. So, we will continue with that in order to find out a limit of twisting, but we will take a different strategy. What is our strategy? We know that twist intensity kappa is equal to pi times d times z, right. Now, what is d? D we know 4 times T by pi mu rho, we already learned in module 2. And what is Z? Z is alpha by root T, is not it? So, finally, what we obtain is that we obtained these 2 root pi alpha by root over mu into rho. right. So, this is another expression for kappa. Now, we will substitute this expression into the expression of yarn retraction. So, you remember we already derived this expression 1 plus pi d z squared minus 1 plus pi d z squared plus 1. So, this is our starting expression in order to derive a condition for limit of twisting. We substitute kappa from here to here pi dz. So, what we obtained 1 plus 4 pi alpha squared by mu into rho minus 1 1 plus pi dz 4 pi alpha squared mu into rho plus 1, right. We obtain this expression. Now, this alpha twist intensity is also related to yarn retraction. How? You remember alpha is equal to alpha naught by yarn retraction. So, that means, in this expression in one side retraction is present, also in the other side yarn retraction is hidden. So, we need to take it out and put it in all in one side, then we will be able to solve for retraction, is not it? We have to basically do that. So, let us do that. Retraction 1 plus 4 pi, sorry, it was 3 by 2, it was 3 by 2, 4 pi squared 1 minus cube mu rho minus 1. You do it step by step, you will make it correct. One, isn't it? Do it slowly, step by step. Okay. So, now what is our goal? Our goal is very clear. We need to find an expression for delta. Now, this delta is here also, here also. So, we need to put all this delta in one side. So, that is our aim, and we will do it slowly. So, then our next step we can write in this manner. Delta into 1 plus 4 pi is equal to minus 1. Right. Okay. So, then we can write 1 plus 4 pi this by 1 minus this p plus this 1 plus 4 pi skis. This is a quite long expression, you do it slowly, but steadily, step by step, you will get the answer. Okay. Now, what we do, this minus 1, it is not good to write in this way, it is called show 1 plus delta is equal to 1 minus delta this, right. So, what we did? We basically put this 1 in this side and we take this to this side. Now, we have to get rid of the square root. So, we have to make square both sides. So, let us do that. Is not it? Right. So, now what we see is that here it is 2, here it is 3, 1 can be cancelled. Oh, we did a mistake. Here is a mistake we did. This is 1 plus, this is also 1 plus, this is also 1 plus. Is not it? So, we have to write it in a different way. So, basically 1 minus this square plus 4 pi this square 1 minus delta mu into rho. Correct? Then 1 plus this square minus 1 minus this square is equal to 4 pi alpha naught square 1 minus mu into rho, right. So, what is this then? 1 plus 2 delta plus delta squared minus 1 plus 2 delta minus delta squared 4 pi squared 1 delta into mu into this. So, what we see here, here these terms are cancelling out. So, what we obtain is 4 delta is equal to 4 pi squared 1 minus into p. This 4 we cancel out, and we can write now all one side pi per squared by mu into rho. Okay. Then we can write square minus this plus this equal to 0. So, we finally obtained a quadratic expression. So, what is the root of this quadratic equation? Root of this quadratic equation is two. So, this is the root of this quadratic expression, right. So, step by step we derived this expression. What does this expression say? This expression is your yarn retraction delta is equal to 1 plus minus root over 1 minus 4 pi alpha naught square divided by packing density mu into rho and whole divided by 2. Okay. Now let us see this discriminant cannot be negative, right. So, it must be greater than or equal to 0. So, let us now write that. So, 1 minus 4 pi alpha naught square divided by mu into rho must be greater than or equal to 0, because this cannot be negative. In that case 1 minus 4 pi square this must be greater than or equal to 0, right. So, this must be less than or equal to 1 by 4 pi. If we take the root, must be less than or equal to 1 by root 4 pi. What is this value? This value is equal to 0.281. Right. Now, if we now substitute 0, then what we will get? We will get let this quantity is equal to 0. It can be 0 or greater than 0. Let us say the minimum value. Let us work on the minimum value, because we have to find out one limit of twisting, right. So, this is equal to 0 minimum value, then what you will get? Half. So, this is the limit of retraction. This is the limit of retraction. Okay. Now, this is the limit of retraction, and we have already found out that tan square beta d by 2, and if the limit of retraction is half. So, tan square beta d by 2 is equal to half, then what will be beta d? Beta d will be 70.5 degree. That means, the twist angle of surface fiber, there is a limit, and that limit is 70.5, right. And then what is your twist intensity? Twist intensity is pi dz, that is equal to tangent of beta d. Now, if you substitute tangent of this, what you will find out? 2 root 2. So, there is a limit of twist intensity also. Okay. So, what we found is that the limit of there is a limit of retraction, that is half. Accordingly, there is a limit of twist angle of surface fiber, that is 70.5, and also then there is a limit of twist intensity, that is 2 root 2. So, theoretically also limit of twisting exists. As I told you, you can determine it practically. It was done in a laboratory. Let me show you the image. Very nice, interesting image. So, this is the actual yarn, actual twisted yarn. What do we do? We put in the twist tester and we try to increase the twist of the yarn. After a few rotation, what you will see is that you will see this kind of image. So, the axis of the yarn will not be straight first, it will happen gradually. First it is straight, almost straight, then the axis deviates from linearity significantly. After a few insertion, you will suddenly see that the structure collapses. So, the fibers, the coils are not absorbed by the yarn, rather they are deposited onto the surface. If you still go on increasing twist, then you will see total disruption of the destruction of the yarn structure. So, it is also possible to determine limit of twisting experimentally, and by using helical model also we have learnt how to explain it scientifically. Now, as we did, every theoretical work must be compared with experimental results. In this case also the theoretical results were compared with experiment, and this is the comparison between theory and experiment. Theory versus experiment. A lot of yarns were studied and along the x axis alpha naught divided by square root of mu into rho is plotted, along the y axis retraction is plotted, and all these points are basically the experimental results for different yarns. And this line, you see there is a continuous thin line going on, that is basically coming from theory. What is this line? You have just now derived root over 1 minus 4 pi alpha square by mu into rho, right. So, this line is the theoretical line and all of the experimental results. What we see is that throughout this region, this theory explains the experimental results quite well. Isn't it? So, this basically completes the lecture part. Now, we will solve a few numerical problems so as to understand the whole theory in a little better manner. Let us start with the first numerical problem. A carded ring spun yarn of 29.5 ticks and 719.43 twist is prepared from cotton fibers of 25 millimeter length and 3 decitex fineness. Estimate the value of coefficient Kn and the number of fibers present in the cross section of the yarn. This you have to solve. How will you solve this problem? Now, what is coefficient Kn? Coefficient Kn we have learned using helical model. The coefficient Kn is 2 by pi dz square root 1 plus pi dz square minus 1. This is your coefficient Kn. So, what you have to determine? In order to find out coefficient Kn, you have to determine d and you have to determine z. Z is given 719.43. So, simply you have to determine d, yarn diameter. How will you determine yarn diameter? Yarn diameter is 4 t by pi mu rho. That is your yarn diameter. T is given. What is T? 4 into T is your 29.5 ticks divided by 3.14. Mu is not given and it is a cotton fiber, this millimeter. So, mu is not given. How will you find out mu? Mu is not given. How will you find out mu? Mu you have to come back to your module 3 in order to find out mu. You remember this formula in module 1, module 3. Now, Q carded ring spun yarn 9.61 into 10 to the power minus 8. We have already solved this problem there. What is Z? Z is your 719.43. And what is your T? T is your 29.5 TX. If you solve this, you will find out mu is equal to 0.46, right. Then you substitute mu here 0.46. So, you will find out diameter is equal to millimeter. This will lead to 0.2318 millimeter. So, you obtain diameter, you know twist, you will obtain twist intensity. So, kappa is pi d z, 3.14 into diameter 2318 millimeter into z. Z is your 719.38. This is in 1 meter. So, this is in millimeter. So, you will obtain kappa, right. What will be this value? 5236. Then you will go back and you will find out coefficient Kn is equal to 2 by kappa squared 1 plus kappa squared minus 1. So, if you substitute kappa from here, you will find out the value 9395, right. So, you in this way you obtained coefficient Kn. The second part of the problem is number of fibers present in the cross section of the yarn. Now, if you know Kn, number is Kn times capital T by small t. So, what is your Kn? 9395. What is your capital T? Capital T is 29.5. And what is your small t? Small t is your 0.3. So, if you solve, how much fiber you will obtain? You will obtain in this case, it will be approximately equal to 93. Clear? So, this is how you will solve problem number 1. So, we are left with 2 more problems. We will discuss those 2 problems in the next class. Thank you for your attention.